So throughout this lecture, we're going to denote for short SOCP for second order cone programming. Now, what is a SOCP? How does the problem look like? So you're going to minimize a linear function, so f transpose x, subject to second order cone constraints that are constraints of the form ax plus b in L2 norm, lower bounded by affine functions. So C transpose x plus d. Now you can have m of those constraints. That being said, you've got m parameters from a down to d. So ai, bi, ci, and di. Now, how do the constraints look like? This is actually requiring that the following vector ai x plus bi ci transpose x plus di. So this has, let's say, k rows, and this is obviously a scalar, so one row. So the following, which is in dimension k plus 1, is required to lie in the second order cone. Of course, in the space R k plus 1. This is all SOCP, right? And if you recall, in the previous lecture, we mentioned that SOCP will actually cover QCQP as a particular case, right? This is not trivial to see because the cost function of the QCQP is quadratic, whereas your cost function in an SOCP is linear. So you might think, oh, this is linear, how come it could cover quadratic cost functions? Well, there's a small trick to it so that you could arrange a QCQP to look like an SOCP. So let's copy a QCQP right here. So a QCQP should look something like this. You're minimizing transpose px transpose less than 0. We forgot here in an SOCP, we forgot the affine, right? The affine constraint. So fx equal to g. I'm going to erase this, or at least throw it out. And an affine constraint here, ax is b, right? So how come a QCQP is a particular instance of the more general SOCP? The first thing you have to notice is that since you're minimizing the function, it's the equivalent of doing the following. So if you have a function f of x and you lower bound it, let's say, by a constant c, right? And your minimization is an x, right? Well, some tricks include that you lower bound your f of x by a constant, and then you minimize that constant along with x. This problem is the equivalent of minimizing with x and c, right? C subject to f of x is less than c. So this and this are equivalent. We're going to do the same thing here. We're going to write an equivalent problem. So minimize with respect to x and c, only c, which is of course linear, right? So now SOCP is starting to show up. We've got linear costs subject to the same constraints, transpose pix plus x transpose qi plus ri less than 0, ax is b, and your cost is less than c, right? The same thing what we did here or here. So x transpose px plus x transpose q plus r is less than c, right? Next, you have to include the norm right here, right? So this norm right here should show on the left-hand side. We don't have a problem with this. There's no problem with this at all because it's already included here. So we've got something in common at least. Now, note that each matrix Pi is actually symmetric and semi-positive definite, right? That being said, you could decompose each Pi into AI transpose AI, square root of the matrix, Pi. And also P is symmetric and positive definite, so P should be decomposed into A transpose A. And one thing here we didn't mention is, there's no restrictions here on AI, BI, CI, nor DI. There's no restriction telling you that AI should be positive semi-definite. It doesn't have to be a square matrix. Why should it be positive semi-definite? So back here, if we replace this decomposition in constraints, we're going to get this. Now, before replacing those decompositions, we also need to do another little decomposition for the Q's. So replacing, we get minimize x and c subject to AI transpose AIX x transpose QI plus RI negative, right? And x transpose A transpose AX plus transpose Q plus R negative, and AX is B. We're getting closer and closer to an SOCP. Now, we need to see where the norm is going to pop up. Note that the norm of an SOCP constraint AX plus B, if we square it, it looks like this. So using the definition of an L2 norm square, which is x transpose x, this guy is going to look like this. AX plus B transpose times AX plus B. That is x transpose A transpose plus B transpose multiplied by AX plus B. If we're talking about real numbers, which is what we're focusing on here, this is easily seen as x transpose A transpose AX plus 2 x transpose A transpose B plus B transpose B. Now, you could actually say that my vector Q could be expressed as 2 A transpose B, right? So with that being said, also the QIs are decomposed as 2 AI transpose B. Replacing those two right here, you're going to get this. Now, why are you allowed to do such a decomposition? Imagine you've got a row Q. All you're doing here is writing it as a matrix times a vector. So if this matrix is full column rank, there shouldn't be any problem, right? This matrix has rank equal to the number of columns, there's no problem. You could express it in whatever bases you want, right? And the 2 here, you can always scale the factors in A, multiply by half, and the 2 outside, whatever. Subject to x transpose AI transpose AIX plus 2 x transpose A transpose BI. Here we have an AI plus RI is less than 0. Then x transpose A transpose AX plus 2x transpose A transpose B plus R negative, and an AX equals to B. So those 2 parts and those 2 parts are actually those parts in the norm. So all we need is a constant, B transpose B. We can add and subtract this constant, right? So right here, you can add plus BI transpose BI and a minus BI transpose BI. Same thing here. You can add a B transpose B, then subtract it, right? So this guy becomes minimize C subject to transpose AI transpose AIX plus 2x transpose AI transpose BI plus BI transpose BI and a minus for x plus RI is negative. Now note that this guy is actually the norm, AX plus B squared. So AIX plus BI in the norm square, right? Likewise, this term is the norm AX plus B all square, right? So we've got a small mistake here. This guy right here, it's due to this. So since this was a C right here, this guy right here should be a C, right? It's not a 0. So it's this guy, and as well, right here. Okay? So now we're going to rewrite this with the norms. Minimize C. I'm going to get those two on the right-hand side. That being said, I'm going to have BI transpose BI minus RI, then AX plus B squared less than C plus B transpose B minus R, and the affine AX equals B, right? Now, we're almost there. This guy right here is a, hence it will play the role of DI, right? So I might as well call this DI. This is a DI, and this guy is also serving as a scalar on the right-hand side, so it's a D. Now I'm not going to fold C inside D because C is a variable in your problem. So remember, this minimization is with respect to C and the vector X. So I'm just going to leave it there hanging for a while and rewrite this again with the D's. So we're minimizing with respect to C and X, only the scalar C, subject to AIX plus BI square less than DI, and then AX plus B square less than C plus D, and then AX equal B, right? So we're almost there, we're not there. And the reason for this is because this variable is hanging outside. So we need to see here just one variable. Let's call it X bar. So X bar is going to be a vector containing X and C in its last element. You can order them as you wish, but this ordering will serve best. So this is my X bar. I should see an F transpose X bar, the cost, as here. So this minimization is with respect to X. I'm going to have an X bar with F transpose X bar, right? How do I choose my F such that F transpose X bar is the cost, which is C? All I have to do is choose F being all zeros except 1 in its last element, and thus F transpose X bar will return C. So the minimization now is with respect to X bar, F transpose X bar, where F is zeros with 1 in its last element, and it should be a column vector, so I'll put a transpose here. Now, with respect to the constraints, let's start with the easiest one, which is the affine constraint. How can I write the affine constraint in terms of X bar? Well, that's easy. All I have to do is say A bar, X bar is B bar, right? Where A bar is nothing other than A and a row of all zeros, where A bar is matrix A with the last column being all zeros, because the C does not show in the affine constraints, so I'll neglect it in that way. Similarly, B bar is B. That's it. Nothing is changing in the rows, so I'll keep it as B. So I might as well remove the bar on the B. Okay, good. That solves this. Now, how do I choose in constraints of the form 1 right here? You could just say you've got AI bars, right? X plus BI square is less than CI X bar plus DI, so that we keep things consistent with the general form right here. I'm including this even though it's not there, so that we see what's the value of CI, right? So CI is clearly 0 because it's not there in 1, and DI is just DI right here, which was BI transpose BI minus RI, right? So I'll copy this here. And what I'm most concerned with is the AI bar in terms of AI. So like we did here, it will be AI, don't forget the bar here, and the transpose here. So it will be AI with a column of all zeros in the last column. And likewise, over here, since C does not interfere with the norm, then we're going to have an A bar, which is the same as this A bar right here, X bar plus B square less than. Now, this is where it's going to get tricky. You're going to have to include C somewhere in your norm, because remember, there's no square here. So when we go down here, since Ci transpose Xi is 0, right? I could remove this and say square root of di. So I square root on both sides, right? And there's no problem here. Then I could call di bar, which is the square root of di, right? So this is di bar. And thus we have this form. Whereas here, if you leave it as it is, and then you do the square root, then you have a variable which you're rooting, which has a square root. And thus, this is not good. It's not what the problem is telling you. There's no square roots in your problem in terms of your variable. There's no square root here. No. So a trick for this, a quick trick for this is, and the reason I'm laughing is because this is how you should, when you have optimization problems, there's a lot of, reformulation so that it fits your problem. I could say I want to minimize a C. Now here it's not going to be the same thing, i.e. we cannot square root on this side and square root on this side because we're going to have one of our variables with a square root. That's not allowed. So what people usually do is that, you're not going to be working in the whole R plus. Numerically, when you want a method that solves your SOCP, your X should be bounded, right? Means your variables are actually bounded. In this problem formulation, we have not bounded anything. We have not bounded our X's per se. Actually, if you come and say one of my variables is bounded, that doesn't violate the QCQP, right? Because if we go back to QCQP, you can express this bounding constraint xi less than a by setting ri to minus a, right? And your qi to a vector of all zeros except 1 at the ith position so that it returns xi, right? And just set your pi to 0 and you're good to go, right? So xi is less than a. So if we come and express one of our constraints as such, there's no problem, right? So similarly, I'm going to do this, but for my C. So right here, I'm going to say C is less than a given bound, which is, I don't know, let's say T. So C should not exceed T. And then this constraint will be redundant. Namely, we can use it here to say this guy is less than T plus D. And now you can do a square root right here. So this constraint will be a bar x bar plus b square is less than square root of t plus d. Note that neither t nor d is a variable. It's just a given constant, right? So this is playing the role of d0, if you will. So to finalize, I'm going to write the final SOCP problem corresponding to our QCQP. So we'll get a minimization over all our variables, namely x bar of f transpose x bar, subject to, I'm going to, denote those as a0, 0, so that we have one line, right? So here I have I going from 1 to m. So I equals 0 will get us here, okay? Just to simplify notation, ai bar x bar plus bi square less than di bar, right? With a bar x bar equal to b and c is less than t. If you want to link the parameters of the problem, this is your f, right? This is d0 bar, so it's the root of t plus d. This is a bar. A 0 bar would then be this, right? And then AI bar is this. Your DIs are such, and your CIs is 0. Well, there's no CI, but whatever. So I'll remove it. And that's it. So finally, what we've learned through all this reformulation is that a QCQP could indeed be seen as an SOCP with no problem. No problem whatsoever. We didn't relax anything. We didn't do an approximation. No, nothing. A QCQP is a particular instance of SOCP. but it's not true the other way around. Well, it's not necessarily true. Some SOCPs could be formulated as QCQPs, but not all of them. What I'm saying here is that all QCQPs lie under the more general SOCPs. Okay? So it's outside QCQPs. Right, so far so good. So up till now, we've defined an SOCP and seen how a QCQP is a particular instance of the more general SOCP. Now let's see one application of SOCP, which is robust linear programming. So a robust linear program is a linear program with an additional constraint. Let me show you how. And to what is it robust? So we're minimizing linear cost subject to some inequality constraints. Now the problem as is just an LP, right? But in some applications, you don't have direct access to AI. That is to say, the vectors AI, so A1 down to AM, are known up to some certain inaccuracy or some uncertainty. One way to model this inaccuracy is by saying that AI lies in an ellipsoid, EI, where this ellipsoid is centered at a certain center AI bar plus an inner product between a matrix pi times a u of norm less than 1. So if you recall in convex sets, when we talked about ellipsoids, this was one way of expressing an ellipsoid of center C while adding a certain direction, q times u, right? So likewise here, AI is known to lie actually in some ellipsoid. This is the center AI bar. So if we're in 3 dimensions, right, then the red vector is your AI bar. Well, AI, the original vector, will rotate pointing here, 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 all the way inside the ellipsoid. The extreme case is when pi is 0 and you're back to L, means that your AI will coincide with a constant AI bar. So in other words, a robust LP, so robust. As you can see, we have one additional constraint which forces our AIs to lie in the ellipsoids, right? We can express those two in one compact statement, which is for all AIs and EIs, right? For I's spanning 1 to n. Now, those constraints are usually referred to as robust linear constraints. And why is that? Well, if we omit EIs, then we're back to linear constraints or inequalities. But when you come and force AIs to fall in EIs, then it's a robust linear constraint. Now, this shows in applications where you don't have direct access to AIs. Note that in linear programs, we are referring here to our FIs, right? So in this lecture, when let's say we solved our linear program using simplex, note that AIs, BIs, GIs, HIs, C and D were all completely known. Note that you can also force any other parameter of the problem to fall inside an ellipsoid to reflect uncertainty. But for simplicity, we're only concentrating on the AIs, right? Now, let's reformulate a bit. Let's go back to this figure right here. This is AI bar, right? So the red ones around are all possible values, or even the one that lies on AI bar. All those red vectors are possible vectors AI, right? Because as we said, AI could span all this region right here. So in other words, if we have a certain inequality AI transpose X less than BI, right? And AI transpose X is a scalar, then this, where AI is an EI, this region right here, we can replace this constraint, or in other words, this constraint, the green one, with a simpler one, which is saying the supremum of AI transpose X, where AI is an EI is less than BI, right? We're picking the max, or more formally, the supremum of this quantity and lower bounding it by BI. This will guarantee that all my AI transpose X will be less than BI, right? Now, let us rewrite this with the supremum. So this is it right now. Now we could rewrite this in a simpler way. That is to say, note that the supremum of the quantity AI transpose X, where AI falls in EI, could be rewritten as the supremum of. Now, if AI falls in EI, we go back to the definition of EI, means that AI will take this form, right? This is the form AI is expressed with. So I'm going to replace it simply with AI transpose bar plus PI U all transpose with X, where the U, or the norm of U, is lower bounded by 1, right? Now let's expand this. So the supremum of I bar transpose plus PI U transpose all multiplied by X with norm of U less than 1, right? Now expanding it even further, supremum of the I bar transpose X plus U transpose PI transpose X, the norm of U less than 1. Note that here, the variable, or the supremum, is with respect to U, right? All this is with respect to U. Previously, it was with respect to AI, right? But now that AI is replaced, U is our variable, if you will. That being said, AI bar transpose times X is now a constant with respect to the supremum. Therefore, it could be extracted outside the supremum. So AI bar transpose X plus the supremum over U of this guy, U transpose PI transpose X, where the norm of U is lower bounded by 1, right? Now we're maximizing this quantity, U transpose PI transpose X, right? And we've seen such a maximization in the previous lecture, somewhere here, yes, when we were using Cauchy-Schwarz. So we said that if we have a quantity of the form C transpose Y, this quantity is maximized only when you pick C along the direction of Y, that is, Y divided by the norm of Y. Well, the same way here, we're maximizing with respect to U, right? So U transpose I transpose X. Now pick here Y as this guy. So this is a U transpose Y. This is your Y. So you should pick U in the direction of Y. That being said, U should be Y over the norm of Y, right? If we replace the value of Y, we'll get that U should be PI transpose X over the norm of PI transpose X. So replacing this value, U star, if you will, in the supremum, we will get, now PI transpose X in norm is a constant and therefore will be extracted. Then we're left with PI transpose X, all transpose times PI transpose X. Now this is a vector transpose with itself, means we will be left with a squared norm. In other words, we will be left with a PI transpose X square over PI transpose X1, if you will, or because there's no squaring, it means we could cancel this with this, and we are left with. So now the robust linear inequality is replaced with something without the supremum. So let's replace it. And my robust linear inequality is as such. There you go. Okay, looks good. Now, guess what? We have an SOCP. So that being said, any robust linear program could be expressed as an SOCP. And in case you don't see it, the SOCP forces a linear objective function of the form f transpose x. So my f is the C, right? And second order constraints are there. So I've got that pi transpose x is less than minus ai transpose x plus bi. So we go back to the SOCP right here. We've got AIs, BIs, CIs, and DIs going down here. So my PI transpose are playing the role of matrices AI, right? I'll write it here. My BI vectors are not there, so they're set to 0. My CI vectors are in fact the minus AI, right? And the DIs are the BIs right here, in case you want to program it in any solver. Oh, and one more thing, the F is the C. And that's it. So any robust linear programming, and not only restricted to one AI, you could also do this to the BIs. You could do the same steps and you reach an SOCP. Right, so we've just seen how to form a robust linear program, which is a linear program with some uncertainty around the parameters of the problem. We've seen how to form this as an SOCP right here. Now, next off, we're going to talk about linear programming with random constraints. So we're going to allow this time our AI vectors to be random. Right here, we allowed them to move in some certain ellipsoid, but now they're going to be random. Those constraints are going to hold some probability. We'll see how. Now, since they're random, means they should follow some distribution function, some PDF. So in that case, we're going to assume that each AI is normal of mean, AI bar, and covariance sigma I. So in that case, we cannot just write this inequality. It doesn't make sense since AI is random, right? So instead, what people do is replace the linear inequality with a probability inequality. So the probability now that AI transpose X is less than BI is greater than a certain threshold or a confidence level, since we are sure that at least at the time AI transpose X is lower bounded by BI, right? And usually eta is picked to be at least 0.5. Now, as we will see, this constraint could be written as a second order constraint. Now, since AI is normal, then so is AI transpose X. So let U denote AI transpose X. So this guy is also normal. The mean of this guy, so the expectation of U, will be the expectation of AI transpose times X. The expectation of AI is AI bar, so we'll have an AI bar transpose X. And the var, the variance of U, will be the expectation of U minus the mean of U, which is AI bar transpose X, all squared. Now, using some straightforward math, we can show that this guy is actually X transpose sigma I X. So with that being said, all this will give us that U is normal with mean AI bar transpose X and variance X transpose sigma I X. We will denote U bar to be AI bar transpose X and sigma square to be X transpose sigma I X. Now this small sigma, not the uppercase sigma. So that we can say U is, a normal of mean U bar and variance sigma squared. Now going back to the random constraint, the probability that AI transpose X is less than BI, we're going to replace AI transpose X with a U, so we'll get a U less than BI. And since U is normal, it's really better to write this as a centered normal. That being said, you subtract the mean of U and you divide by sigma on both sides. Why do we do that? So that this guy is now a centered Gaussian. So if we call this Z, if you've taken any statistics courses or probability courses, the Z, you could easily look it up in the Z table. Well, this is usually denoted as phi at the right-hand side with respect to the centered Gaussian. So phi bi minus u bar over sigma, right? Where phi of z is nothing other than an integral going from minus infinity up to the argument, because this is a probability less than. So if this is a centered Gaussian and this is my bi minus u bar over sigma, or the argument, then it's all this shaded area. Means that it's going from minus infinity up till this bound, bi minus u bar over sigma. Of what? Of e minus x squared over 2. So there's no mean, zero mean, and a unit variance. So we should divide here by a square root of 2 pi dx. Now this is also referred to as the commutative distribution function, because we're integrating a PDF, so we're going back to the CDF. So the probability that AI transpose X is less than BI is written as phi of BI minus U bar over sigma, right? Should be greater than eta. Now, since, phi is an increasing function, so the more the argument increases, so this is a Z, so this should be a Z. Sorry about that. The larger Z is, the more area we'll cover. So a CDF will be an increasing function. Since it's an increasing function, we could apply phi inverse on both sides. So we'll get a BI minus U bar over sigma greater than the inverse of phi of eta, right? Now organizing terms a bit, multiplying by sigma on both sides, we'll get a BI minus U bar greater than sigma phi inverse of eta, right? I'm getting your U bar here. You will have a U bar plus sigma phi inverse eta less than BI. Now replacing U bar with its corresponding equation, which is this, and sigma with its corresponding equation, which is this, we will get an AI bar transpose X plus, be careful, we had a sigma square equal to X transpose sigma I X. That being said, sigma will be the square root of this. So square root of sigma I. We're going to replace this here. And this is also, you could write it as X transpose sigma I half, sigma I half. The norm of sigma I half X square. With the square root, you'll end up with a norm sigma I half X without a square, right? We're going to plug this here. So the norm of sigma I half X multiplied by phi inverse of eta less than BI, right? And there you go. So we're going to replace this with the last problem formulation. We have this, and we will get following problem. So minimizing C transpose X subject to this guy. The I bar transpose X plus the norm sigma I half X times a certain factor lower bounded by BI. Now here we have the norm term, and here's the linear term, which will go on the right hand side. So, okay, so the right hand side is looking good. The left hand side, you might nag about this term. Well, we can divide by it. So minimize transpose X divide all sides by phi minus 1 eta. We'll end up with only a norm on the right hand side, lower bounded by minus AI transpose x over phi minus 1 eta plus bi over phi minus 1 eta, right? And there you go. This is an SOCP. Why? Again, linear cost SOC constraint. Your AI in the SOC problem is your sigma I half, your bi is a 0, your ci is this vector right here, so it's a minus AI transpose divided by phi minus 1 eta, and your di is all this guy, bi over phi minus 1 eta. Finally, your f is the c. So up till now, we've seen two applications of SOCP, that is robust linear programming, which could be casted as an SOCP, and a linear program with random constraints. Now, the latter, you find it a lot in portfolio analysis and more specifically in the Markowitz portfolio analysis. So another application of SOCP lies in the classes of problems that involve sums of norms. That is to say, consider the following unconstrained problem. That is, minimize simply sum of L2 norms, summation of AI x plus bi without the square, right? So an L2 norm. Of course, the minimization is with respect to vector x. Now, this problem could be easily casted as an SOCP, and we say that each term now of AI x plus bi in a norm is lower bounded by the term ti. That is to say, AI x plus bi in L2 norm is less than ti. That means that the sum on both sides, since all the terms are positive, then there's no problem in summing on both sides as such. So instead of minimizing this, I'll minimize an upper bound. So I've got the following problem now. Minimizing x and ti's, so I'll call it vector t, where t is the vector t1 down to tp, right? So we're going to minimize the sum of ti's subject to each constraint of the form AI x plus bi will be lower bounded by ti, and there is m such constraints, or p. Let's stack both in one vector, call it x tilde as such. So we're going to have a minimization in x. Write this as f transpose x tilde. All you have to do is choose f to be a vector of zeros of dimension n, that is the size of x, right? And the rest, which are p, choose them all ones. And thus you can verify that f transpose x tilde is nothing other than the sum of ti's. So this is our f. I'll just write f transpose x tilde as such, subject to, and I want to see this only as a function of x tilde. Of course, in AI, bi, and some constants, but I don't want to see x and ti's. I want to see only x tilde, so that we have a concrete SOCP problem. So how do we do that? Since here we only have AI x, as we did before, let's call AI bar, which will contain AI in its first columns and zeros in the others. So we're going to have AI bar x tilde plus bi in L2 norm is less than ti. Now ti, how do I write this as a function of x tilde? Well, that's easy. Let's call a vector ci, which will be transposed with x tilde, and each time a ci transpose x tilde is going to return a ti. How do we do that? All you have to do is choose a ci which contains zeros as f in its first n entries, right? And then over here, right beneath the all zeros, we've got a vector EI. And what is EI? It's the classical basis. That is, it contains zeros except one in its ith entry. This means that each time Ci transpose x tilde is going to return me a Ti. And we've got P of those constraints, and there you go. This guy is an SOCP. That's it. By the way, over here we could have done the same thing. Instead of forcing C to be less than T, we could have said C is X bar. X bar is my variable now, where it contains C in its last entry, right? So all I have to do is multiply by a vector EK, where EK contains zeros except one in its last entry, right? In that case, X bar transpose EK is C. And therefore, we're going to have here an EK transpose X bar, and thus the problem is an SOCP. So where do you find applications of this? There's a known problem which is called the Steiner tree problem, and this is named after Jacob Steiner, big guy. This guy is a Swiss mathematician who worked in geometry. So in this type of problem, you've got something called a Steiner tree. So you're given a graph, right? And a subset of vertices in the graph. So let me just give you a small example. Consider I've got A1, A2, A3, and A4, right? And they're all connected with some costs on their path. So 5 here, 2 here, 10 here, and let's say there's a 20 here. And let's say A1 and A4 are termed as terminal vertices. So here the minimum Steiner tree for this graph is clearly 2, 10, this path right here. This is a combinatorial problem. There's a lot of heuristics to solve it. And one concrete way of dealing with this is to use an SOCP formulation of the sum of norms, because each norm is going to, at the end of the day, reflect a distance right here. So another application of SOCPs would be problems that involve, instead of sum of norms, we'll have the max of norms. Instead of minimizing the sum of the norms as we did before, this time we're going to minimize the maximum of the norms, maximum over I, right? Because we've got P of such terms, so we're trying to minimize the maximum. Well, in that case, you also have an SOCP, and why is that? Well, in a very similar manner, you could say that let's upper bound the max of the norms by a parameter T, right? And instead of minimizing the max, you minimize only T. And thus, the problem we're looking at right now is a minimization with respect to vector x and the scalar T. So we're minimizing T instead, subject to max I of AIX plus BI. And that's what we're looking at, right? Now, the classical SOCP does not have a max here, but what does this inequality mean? If the max of the norms, right, is lower bounded than T, then what could you say about each norm separately? It's also less than T, because if you upper bound the maximum of numbers, means that each and every one of those numbers is lower bounded by the upper bound, right? So instead, you can write this subject to the same exact problem we had, but this time without the max, and now we have P such constraints. As we did before, this is linear, this is an SOC term, and this is a linear term, and the same steps as we did in the sum of norms, you could formulate this as SOCP. Okay, so far we've covered a lot of problems that could be formulated as SOCPs, such as a QCQP, robust linear programming, or linear programming with random constraints, and problems involving norms, that is, sum of norms or the max of norms. Another really important problem that could also be formulated as SOCP are those that contain hyperbolic constraints. So assume that we're minimizing the following sum of linear fractions, so 1 over AI transpose x plus bi, right? Subject to that the denominators are positive and that we have some other linear inequalities. So we've got p such denominators since the sum is going from 1 to p, and we've got, let's say, q other linear inequality constraints. Now note that this is still convex. Linear fractions are convex. So note that this cost is also referred to as a harmonic mean. Harmonic mean is simply the mean of the reciprocal of a bunch of numbers. So say I want to compute the harmonic mean of x1 down to xn, then it's nothing other than n over 1 over x1 plus 1 over xn. Well, here it's as if we're minimizing, the harmonic mean of functions of the form A transpose X plus Bi. So this is a harmonic mean of an affine transformation of X. And we've got a bunch of linear inequality constraints that will form so-called polytope. So we're minimizing a harmonic mean of an affine transformation of X over a polytope. We can, as we did before, introduce some variables that will linearize my cost. That is, we can bound 1 over AI transpose X plus Bi to be less than Ti. That is 1 less than Ti AI transpose X plus Bi, right? We can introduce this as a constraint to the problem, and hence the problem could be the equivalent of minimizing sum of Ti's subject to this constraint right here. So, and this constraint right here. And since the denominator is positive, then we can say the same thing about Ti. And hence, here we can say Ti's are also positive. I going from 1 to P, and here my I is going from 1 to Q. Now, this by itself could not be written as an SOCP. Why? Because we see that Ti, which is a variable of the problem, and x, which is another variable of the problem, are multiplied by each other. And hence, it's hard to write this as an SOC constraint, right? Well, there's a classical inequality, let's put it that way. It's not hard to prove. We have to pay attention to the following. So let's say I've got a number, w, such that w squared is less than xy, right? Where x is non-negative, and so is my y. Then this is the equivalent of the following inequality. So in the norm, this vector 2w in the first entry and x minus y in the second entry is upper bounded by x plus y. So a generalization of this inequality to vector notation, to vectors, will be for a vector w, let's say w falls in Rn, and we've got two numbers, xy is in R plus and y is in R plus. X and y are still scalars. Then we can say the same thing. Instead, now that here the vector is of size 2 by 1, well, now my vector will be of size n plus 1, right? N coming from here and the 1 from here. So this guy is less than x plus y. Simple as that. Now I'm going to use this version of the inequality in this constraint. Well, it's not hard to see that Ti will play the role of x, AI transpose x plus Pi will play the role of y, and w square will be 1. So if I pick it as such, then this inequality, which is w squared less than xy, where x is positive because Ti is positive, and AI transpose x plus Pi is positive due to this, combining those three conditions, we're going to get this norm right here. Okay? Now let's use this norm in one of the constraints, minimizing with respect to x and the t vector, where t is t1 down to tp, the sum of ti's subject to, as we said, I'm going to copy W squared is 1, or W is 1, X is Ti, and Y is AI transpose X plus BI over here. I'm going to plug those values over here, and then I'm going to copy it as a constraint. So I'm going to get 2W, which is 2, X minus Y, which is Ti minus AI transpose X minus BI, less than X plus Y. That is Ti plus AI transpose X plus BI. And I've got P such constraints. Let's not forget the other linear constraint where I've got Q such constraints. Now this guy is an SOCP. Why? It's not that hard to see. We can write it. I'll forget about this constraint right here for a moment. Let's focus on this one. We can write this in the form of AI x bar, where x bar is going to contain all my variables, x and t, plus bi is less than, I'm not going to use ci transpose plus di because I already used it here. I'll use gi transpose x plus hi. Okay, so how do we achieve this guy right here using a x bar plus bi? Well, we can pick, if this is my AI, I can pick an AI such that its first row is all zeros, and a BI such that if I compute AI x bar plus BI, the first entry will be 2, right? And now, so that I pick the second entry to be TI minus AI x plus BI, how do I do that? Let me call this an FI, because we already used the BI here, right? Just for notation's sake. So plus FI, and this guy will be my FI, okay? And now, if my x bar, we're going to try to pick Ti minus AI transpose X minus Bi. So Ti is easy. All I need to do is stack an AI, I have to zoom here in a bit, such that its first n columns are all zeros, and then an EI right here, where EI is zeros except 1 in its ith entry. So in that way, this row times X bar will return Ti. Okay, good. Now, how do I pick AI transpose X minus Bi? I'll replace the zeros by a minus AI transpose. So my AI is of size 2 by n plus p. We said here we have zeros, so the zero vector. Right here we have the minus AI transpose, and right here I have an EI, right? And this will force us to pick the second entry of Fi to be minus BI. Now you can go ahead and verify that AI x bar plus Fi, this norm, is actually this. So this is norm of AI x bar plus Fi. And it's not hard to see that this guy is easily GI transpose X plus HI, where GI is AI and HI is TI plus BI. This linear constraint, I'm not going to talk about it. It's really easy. All you have to do is see this as an SOC as well by picking your AI to be 0. Your BI is also 0 because we have no norm right here, so it's 0. And your CI and VI are already there, okay? So a linear constraint is a particular case of an SOC constraint. No need to elaborate on that. So there you go. So we're not seeing in this lecture how to solve an SOCP. We're formulating a lot of hard problems or problems that are not trivial. As SOCP, we're collecting all such problems. And by next lectures, we'll see how to solve SOCPs. So we've seen how to formulate a problem with hyperbolic constraints as an SOCP. Other problems that show hyperbolic constraints, I should have included it in this column, but I'm going to exclude it from this column. The quadratic fractional problems. So problems of the following form, just minimize sum of, instead of a linear fraction as such, as we saw before, over a polytope, so AI transpose X plus BI being positive and some other linear inequalities forming a polytope. So instead of this, I've got a quadratic term in the numerator, so Fix plus GI squared. This problem, same as before, could be formulated as an SOCP. How? Just first bound this by Ti, so this is the equivalent of minimizing sum of ti's subject to, since each term of those is less than ti, then we are going to include it in the constraint. And since this is positive, the denominator and the numerators are positive, then ti will also be positive. So we're not going to touch this constraint. And I'm not going to argue this constraint for the same reason as before. This is a linear constraint, and thus it is an SOC constraint. So we're not going to talk about this. There's no need. Now this, we can rearrange it as we did before. So minimize sum of ti's, multiply by ai transpose x plus bi on both sides. Now this guy we could also use for this term right here the second inequality. So this one, that was a dark color. I'm going to copy it on this corresponding column anyway. So for w and rn and x positive, so is y. If w transpose w, or in other words, the norm of w squared, we've got this right here, is less than xy, so this is x, this is y, this is the vector w, then we can say that this inequality right here is the equivalent of 2w in the first entries with x minus y right here. The norm of that, actually this order doesn't matter. However you order your vector, the norm is unchanged. So the ordering doesn't matter. I could have put x minus y in the beginning. It's not going to change anything. So less than x plus y. We're going to use this instead of this. So copying the equivalent problem, we will have to minimize same cost subject to the following. So 2w, that means we've got 2fi x plus 2gi, and then x minus y, that means I've got a ti minus ai transpose x minus vi. The norm of all this guy is lower bounded by ti plus ai transpose x plus vi. P such constraints, Q of those linear constraints. Pick this guy as an ai x bar plus vi. And here it's easily seen as a linear constraint, so gi transpose x plus hi. You can easily pick those, and hence this is an SOCP. So that's it for this lecture. I hope you found it beneficial and useful. We've covered a whole lot of stuff, starting from SOCP formulation down to seeing why QCQP is a particular instance of SOCP. And we've seen a lot of, I would say, applications to SOCP. They could also be, we've done a lot of reformulations towards SOCP. Namely, we've casted well-known problems in optimization towards SOCP. To mention a few, we've done some robust linear programming and linear programming with random constraints. Next off, we've seen how to form a problem that involves sum of norms as an SOCP. And an application of sum of norms is the Steiner tree problem, where the problem is to find, where given a graph, you should find the minimal way to traverse terminal vertices. We've also seen problems that involve max of norms, so that also could be casted as an SOCP. And finally, we've talked about problems with hyperbolic constraints, which was a particular instance of quadratic fractional problems. You just set your fi to 0 and gi to 1, and you're back to this linear or harmonic affine mean of x. So yeah, those two problems happen to also be SOCPs. Other problems that we did not cover in this lecture, but hopefully we will see it in future lectures, are problems that include logarithmic Chebyshev approximation problems, matrix fractional problems, SOC representable functions, so functions in general functions that could be also seen as SOCP problems, and robust least squares. So it's a generalization of the robust linear programming here. So your objective would be to minimize a norm where your parameters involved are known with some certain accuracy. So yeah, that's it for this lecture. If you want to receive future notifications about this channel, please make sure you subscribe to the channel and hit the notification button. And if you have any comments, just leave it in the comment section down below. And yeah, that's basically it. I'll see you then.